Okay, so in this chapter, we're going to talk about fluids. Okay. In all our cells, you have liquids. Your cells are surrounded by liquids. Um, we move through fluids, and marine animals move in water. They're moving through fluids. So biology depends on fluids. Okay? Life depends on fluids. And so we want to understand the properties of fluids. Okay? So cells and organisms are filled with fluids, whether air or water. Fluids are liquids and gases. Okay? So larger plants and animals have developed circulatory or vascular systems. I guess so. What we mean by that is, if you're a large animal. Yeah, so I'm just going to. So if you're a large animal, so here's a cell. Okay, in a cell, all the nutrients and gases go through diffusion into the cell. And diffusion can only transport stuff over very small distances. Okay, so if you are a large animal, to get nutrients and oxygen to the cells, what you have to do is you have to develop plumbing. Okay. Vascular systems bring nutrients near the cell, and then the nutrients and oxygen near the cells, and then it's transported via diffusion. Okay. Within the cell itself, you have liquids and molecules are transported from one region to the other region via diffusion. Okay, so you have to know properties of fluids. Okay, so that's what we mean by so large plants and animals have developed circulatory system, okay, plumbing, or vascular system that use fluids to transport. They use fluid to transport vital nutrients and dissolved gases to cells. Okay, so you're using blood to transport nutrients and oxygen to cells. Okay? So the physics of fluids often makes spectacular demands on organisms, and so organisms have evolved to obey the laws of physics. Okay, well, you have to obey the laws of physics of fluids. So we'll talk about alveoli in your lungs. Okay, so for instance, an alveoli is a fraction of a millimeter big, and that's where these are in your lungs. Air gets in there. So they have the properties. So alveoli, you can think of them as rubber balloons. And here's the amazing property of them. As the alveoli fills with air, gets bigger, you don't want this to expand too much. So what happens is this rubber gets stiffer, preventing it from expanding too much. And when you breathe out air, you'll see that they get smaller. And if the rubber was stiff, then the alveoli would collapse. And you don't want that happening. So how would you prevent the alveoli from collapsing? The rubber becomes softer. Okay? So the surface tension of these alveoli changes, okay, as you're breathing in and out. Okay? And we'll talk about how that happens. So it's pretty amazing. Okay? The proper functioning of alveoli in lungs depend on the smooth flow of air into and out of the lungs, and on surface tension, which changes. Okay? So we'll see how the surface tension, that is the stiffness of this balloon, changes. Okay, so what needs to happen? As it expands, it needs to become a stiffer balloon so it doesn't you don't have runaway expansion. And as you breathe out, as it collapses, if it were stiff, the alveoli would collapse. And you don't want that happening. So it becomes a softer balloon. Okay, so pretty amazing. All right, life depends on fluids. Blood flows through our bodies. Cellular processes operate within intracellular fluid. Okay, so all your cellular processes are occurring in the intracellular fluid inside the cell, the fluid inside the cell. Okay, and so on. A fluid is a substance that flows. So fluids are gases and liquids, they flow. And now let's look at the difference between gases and fluids. In a gas, you see the molecules are well separated, and they do not interact until they collide. Okay, so a gas is compressible. You can compress a gas. In a liquid, the molecules can flow about, but there's bonded strongly, not as strongly as in a solid. Okay, and so, but there's not space between the molecules. So a liquid is incompressible. A gas is compressible. Okay. In a gas, each molecule moves freely. A gas is compressible. Okay. In a liquid, the molecules are bound to each other, but not as strongly as in a solid. The weak bonds keep the molecules close together, but they allow them to move. So this molecule can move anywhere. In a solid, the molecules are fixed in fixed locations. You can come back 10 years from now, and that molecule will still be there. Okay? So in a liquid, those molecules are ever moving. Okay? So that's the difference between liquids and solids. All right. Now we'll define the density of a substance. The density is denoted by rho, this Greek symbol. Okay. And the density is mass per unit volume. Okay. So the density is a property of the material. So for instance, you can take a block of copper, break it up into pieces. The mass of each piece will change, the volume of each piece will change, but the density of all pieces will be the same. Okay? So the density is a property of the material. Okay, so air has a density of, so these densities are in kilogram per meter cube. Air has a density of, at 0 degrees Celsius, has 1.3 kg per meter cube. So this is a meter cube right here. This much air is 1.3 kgs. 1.3 kgs is roughly about 3 pounds. That much air weighs 3 pounds.
At sea level.
At sea level, yeah, this much air at 0 degrees Celsius. Okay. Look at the density of water. Water is 1,000 times more dense. So water, this much water weighs 1,000 kgs. That's roughly the weight of a small car. Okay. What that means is, okay, so the density is 1,000 times greater. Okay. And so the volume is the same, the mass is 1,000 times greater. What that means is, if in air the molecules are this far apart, in a liquid, in water, they're 10 times closer. Okay? So that's what that means. And let's look at the density. They don't give you the density of, so the density of blood is slightly greater than the density of water because there's stuff in blood. Okay, blood is water and stuff. You'll see that the density of metals is about 10 times greater than the density of water. It's about 10,000 kg per meter cube. Okay, so here's the rough rule. Liquids have densities about 1,000 times greater than gases, and solids have densities 10 times greater than that of liquids. Okay. So anyway, these are various densities. Now, liquids exert pressure. So if you have a liquid like this, this liquid exerts a force on this area like that. And actually, so if you look at this liquid, so this part of the liquid exerts a force on this part of the liquid, and this part exerts an equal and opposite force. Okay, so liquids exert force in every direction, and they exert a force perpendicular to the surface. Okay, so there the force is exerted like that. Here it's exerted like this. Okay. Pressure is defined as the force per unit area. Okay. So for instance, air also exerts pressure. Okay, so air exerts pressure like so. Let me show you an app. Okay, so here's this gas at 30 atmospheres. 1 atmosphere is 15 psi. Okay, do you guys know what that psi means? Anybody?
Pressure per square inch.
Okay, 1 atmosphere is 15 psi. Yeah, so what this means is pounds per square inch. Okay, so here's 1 square inch. This air bouncing off the walls is exerting a force of 15 pounds per square inch. These air molecules that are extremely light are exerting a force of 15 pounds per square inch. Okay, that's an enormous force. We'll talk, so let's talk about that. So for instance, this iPad is 10 inches by 10 inches. That's 100 square inch. Okay, so pressure is force times area. So the force is pressure times area. Okay, so on this iPad, the air is exerting a force of pressure is 15 pounds per square inch. And the area of this iPad is 100 square inches. So the air on this iPad is 1,500 pounds. Why isn't this iPad flying away? 1,500 pounds is the weight of 10 people. Same thing is happening on this sheet of paper. There's 1,500 pound force on this guy. Why isn't this guy flying away? Okay. So there's an equal 1,500 pound of force here. And that's why it's not flying away. Imagine the same thing. Air is pushing down on you. Okay, there's a force equal to roughly the weight of a school bus on you. Why aren't you getting crushed? Because inside there's an equal pressure. Okay. Same thing, and that's why you don't even think about it. You can move through air like nothing. There's a huge force on you in this direction, but there's an equal and opposite force in this direction. That cancels it, so you don't have to worry about it. Okay. All right, so pressure is defined as so pressure is force per unit area, and the units of pressure are units of force. SI units of force are newtons, and area are meter square. So this unit is a Pascal. Okay, PSI is a different unit, so the SI unit for pressure is pascals. Okay. And we'll come to those units, other units in a while. Okay. All right. So fluids exert a force perpendicular to the surface. So fluids always exert a force perpendicular to the surface. Okay. Okay, what this illustrates it in a little bit, we'll learn that the pressure in a fluid increases with depth. Okay, so what is happening here is the pressure here is larger than the pressure outside, which is atmospheric pressure. And the larger the pressure difference, the faster the fluid comes out. Okay, so here the pressure is not as high, the fluid is not coming as fast, and so you see it doesn't fall too far. Here the pressure is higher and the fluid is falling further up. Okay. Oh, this diagram is not good. So this should fall like that, this is like that, and this should, okay, this, it's coming out faster, but it doesn't have enough time to go further. It hits the ground, okay? So anyway, you see, the deeper you are, the faster the liquid is coming out, okay? And in fact, here's an interesting fact. This speed at which the liquid is coming out is equal to the speed at which you would drop this thing. So if you, for instance, this is very interesting, if you drop a keychain, let's say you drop a rock, and if it falls this far, the speed at which it's going is exactly equal to the speed at which the liquid is coming out. Okay. So if you drop a rock and when it's fallen this far, it's going at a certain speed, that's the speed at which the liquid is coming out. Okay. So, and that's assuming there's no viscosity, but in this case, viscosity can be neglected. So atmospheric pressure is the pressure the air exerts, okay? And this atmosphere exerts a force by bouncing off the walls. There are billions and billions of collisions happening every second. And like you saw, there's 15 pounds of force every square inch, okay? And now you can see, okay, so what I'll do is the temperature controls the speed of the air molecules, gas molecules, okay? So if you keep the temperature the same, the speed is the same. But now I'm going to add gas. What is happening to the pressure? The pressure increased. Why did the pressure increase? Why do you think the pressure increased? It's very logical. Can you figure it out? That's right. More molecules are bouncing off the same wall per second. More molecules they're bouncing off the wall at a greater frequency, and so the pressure increased. Yeah?
Wouldn't the molecular friction also increase the temperature?
No, the temperature is just a measure of the average speed of the molecules, and that's not increasing. Okay. So the greater density of molecules increase the frequency of collision, and so the pressure increased. Okay. All right, why do we care about that? So here's why. Okay, it turns out that the density of air decreases exponentially as you go up. Okay. So if you go to space that's about 60 miles up, the density is almost zero. So the pressure here is almost zero. Okay. The pressure decreases exponentially. Okay. So in fact, the density in Denver, which is a mile high, is about 83% the density here at sea level. So the pressure in Denver is 83% there. That means oxygen in Denver is about 83% the oxygen here. Okay. All right, so the air pressure in Denver is about 83% that in Miami. The atmospheric pressure at sea level varies slightly with weather. Even the pressure here, the density of air varies with weather, but the global average sea level pressure is it's called 1 atmosphere, and it's 100,000 pascals. It's 100,000 pascals. So 1 atmosphere in pascals is about 100,000 pascals. And you saw that it's about 15 psi, pounds per square inch, okay? And it's also called roughly 1 bar. Okay, so those are some of the different units used to measure pressure. All right, so we already mentioned this. Okay, the pressure is 100 kilopascals. You might wonder why the weight of the air doesn't crush your forearm when you rest it on a table. So here's your forearm resting on a table, and let's calculate the force on your forearm. Okay, your forearm has a surface area of 200 centimeters square. So force is pressure times area, and area of your forearm area is 200 centimeters square, which is 0.02 meters square. Okay. And the force is pressure is 100,000 Newton per meter square times area 0.02 meters square. Okay. And this is, so borrowed 100 times this is 2, and so, and then you're left with 10 to the power of 3, so that's 2,000 newtons. Okay. So when you're resting your arm on a table, the force on you is 2,000 newtons, which is 450 pounds. So when you're resting your arm on the table, the weight, the force that the air exerts is 450 pounds, the weight of 3 people. Okay? And the reason your arm is not getting crushed is because that the air underneath your arm is exerting an equal and opposite force. Okay? How's that little tiny bit of air exerting that force? Because of the bouncing. Okay? All the air bouncing off your underarm is exerting that force. Yeah. So again, like we said, fluids exert forces in all directions. There's a downward force on your forearm, but the air underneath your arm is exerting an upward force of the same magnitude. The net force is close to 0. And that's why, you can walk around without thinking about it. The air in front of you is pushing you backward, and the air behind you is pushing you forward, and those two forces are canceling each other. Okay? The fact that we are surrounded by fluid allows us to move around in air, just as we swim underwater, oblivious of these forces. So, and also the fluid pressure inside your body must be very close to 1 atmosphere to prevent you from imploding or exploding. Okay. So, now you might, so we'll see in a second that, so you can think of the atmospheric pressure as the weight of this air column. Okay. And now if you go underwater, for every 10 meters you go, the pressure increases by 1 atmosphere. So if you're 10 meters underwater, 10 meters is 33 feet underwater, the pressure is 2 atmospheres. All right, so let's say you go diving. Okay, now you're 33 feet underwater, or 10 meters underwater, and now the pressure crushing on you is 2 atmospheres. So the force doubled on you. So how come you don't get crushed? How come your lungs don't get crushed? So to prevent your lungs from getting crushed, what do you have to do? Now you have to breathe air at 2 atmospheres. Okay, so every 33 feet you go down, you have to breathe air at an additional atmosphere. Okay. Now here's the problem. You breathe air at a higher pressure, it's like in your soda, there's gas mixed in the soda. Okay, so carbon dioxide and all those gases get mixed in your blood. And if you came up too fast, all those air would bubble up in your blood, and those bubbles would be in your joints, and that would hurt like crazy. Okay. So you can't come up fast, you have to come up gradually, so the air doesn't bubble up and it's released through your lungs. Okay. All right, so like I said, the pressure increases for every 10 meters, the pressure increases by 1 atmosphere. Okay. So here there are submarines. So Alvin is a research submarine, and the ocean depth is, ocean floors are roughly about 4 kilometers deep. Okay. So, and this Alvin can go to the ocean floors, and so if you go 4,500 meters deep, that's about 4.5 kilometers. The pressure is 450 atmospheres. That is 7,000 psi. Every square inch of the submarine is feeling a force of 7,000 pounds. 7,000 pounds is the weight of 7,700, 50 people. Okay, so that's an enormous pressure. Okay, so if you're installing windows, so here's a submarine and you want windows installed so you can look out. The windows have to be like this. So here's a side view. The windows sit in a conical slot. Okay, so the higher the pressure, the harder it's getting pushed into the slot, and so the seal is guaranteed to be good. Okay, and that's what this is. So there's this window, and this guy is making sure that it has no cracks or any defects. Okay, so installing a window in a craft that goes to this depth is no mean feat. A technician inspects the window that will fill a viewport. So this window will fill this viewport. Okay. The tapered shape will have its larger face facing the sea. The water pressure will push the window firmly into its conical seat, making a tight seal. Yeah. So we already saw that atmospheric pressure exerts enormous forces. So again, what is the force on this sheet of paper? It's 1,500 pounds. Okay. So now we'll show you another example. So here's a suction cup. Okay. And a suction cup is held to the ceiling by air pressure. So what does a suction pump do? What does it do when you use a suction pump?
Move the atmospheric pressure on one side so that the imbalance holds it in place.
Okay, so when you push this suction cup against the wall, you might have used this when you stick stuff in your car windows and stuff like that. You've used little suction pump. When you push that, what it does is it drives away the air behind it. All the air is driven away. So now the air can't push you this way, so there's only air pushing you this way. Okay? And now let's see how much weight can you hang. So this is the air pushing this suction cup against the ceiling. There's no air inside behind the suction cup to push you back. So that thing is sticking to the ceiling. Okay? So the air pushing you up is holding you to the ceiling. Okay. The suction cup is 10 centimeter diameter. 10 centimeters is 4 inches. So it's about this big. The suction cup is about this big. You stick the suction cup to so as big as that light bulb. You stick a suction cup like that, and if it's a good seal, the weight that can hang from there, okay, so here's the suction cup. The force of the air is air pressure times, so assuming there's no air in there, this air is pushing you up, force times area, pressure times area, and this pressure is 1 atmosphere, 15 pounds per square inch, and that should equal the weight it's supporting. Okay. And if you calculate that, the weight turns out to be 81 kgs. That's more than your weight. So you have a suction cup like that on the ceiling, you can hang on to it. Okay. You guys might have seen bicycle racks for cars that have these suction cups, and you can drive 80 miles an hour and that bike won't come off the rack. So that thing is hanging on to the. Okay. So suction cups, if they're good, they work really good. Okay. So what is it that you got to make sure? The seal is tight. The minute air leaks in, that thing is falling off. Okay. So All right, now we'll talk about how the pressure increases with depth. So here's a liquid in a liquid. Okay, so here's atmospheric pressure. Okay. And what we want to know is what is the pressure here. Okay, so here's the atmosphere pushing you down, and there's the weight of this liquid column. Okay, so what you have to do is you have to support the force due to the atmosphere plus the weight of the liquid column. Okay, so what you have to do is the force of the air, this force is equal to P naught A plus the weight of this liquid column. The liquid weight of this liquid column is, in terms of the density, it's rho times the height times the area of cross section. This is the mass of this liquid column times gravity, and that should equal the pressure times the area. That should equal this force. So this force plus the weight should equal that force. And if you cancel out the area, you get the pressure at the bottom. And the pressure at the bottom is P naught, the atmospheric pressure, plus the density of fluid times G times this height. Height is written as D here. So as you go deeper, the pressure is increasing. Okay? And you can calculate this for every 10 meters of water, this is equal to atmospheric pressure. Okay? So every 33 feet you go down or every 10 meters you go down, the pressure increases by 1 atmosphere. So for 10 meters it's 1 atmosphere, another 10 meters, another atmosphere, and so on. Okay? So this is how the pressure increases with depth. All right, so here's you're swimming underwater. Okay, now as you're going deeper, the pressure is increasing, and here's your eardrum. Okay, so water gets in your ear canal and it's pushing on your eardrum. Okay, so let's say you're diving 5.5 meters. 5.5 meters is roughly the height of this ceiling. Okay, so if you're this far underwater, the pressure on your eardrum has increased, and let's see how much it's increased. Okay. So what this shows you is, so there's the pressure at this depth, and the pressure at that depth is 160 kilopascals. So here it's 100 kilopascals, so at a depth of 5.5 meters, it's 160 kilopascals. Okay, the pressure has increased by 60%. If you went 10 meters, it would be 200 kilopascals. Okay. So the force of the water on your eardrum is the pressure times the area of your eardrum, and this is the area of your eardrum. It tells you. So the eardrum has a typical diameter of 8 millimeters. 8 millimeters is about that much. So that's how big your eardrum is. Okay, less than a centimeter. It's 8 millimeters. Okay, so that's the area, and there is the force on your eardrum. Okay, now let me draw the side view of your eardrum. So here's your eardrum, which is okay, and there is this water pushing you with a force of 8 newtons. Okay, 8 newtons is roughly. It's roughly 1 kg. 1 kg is 2 pounds. So the water is pushing your eardrum with 2 pounds force. Yep. Now that could damage it. Okay, but of course there's in your inner ear there's air, but this air is at 1 atmosphere. Okay, that's pushing the eardrum back in that direction. Okay. So this inner ear, the air pressure is 1 atmosphere. Okay, and so this pressure is this force is 5 newtons. So here's 8 newtons pushing you, and so this is 5 newtons pushing, the air is pushing at 5 newtons back. So there's a net force of 3 newtons in this direction when you went diving. Okay. All right, so here's the deal. Why is this at 1 atmosphere? So when you're diving, the water is pushing you, and so the pressure in the lungs is also 160 kilopascals. So your lungs compressed, and that air pressure is 160 kilopascals. But what is the deal is this is eustachian tube is normally sealed. Okay. So what you want to do is force air from your lung to the inner ear and bring this pressure to 1.6 atmosphere. Okay. And then the forces will be balanced and your drum won't be damaged. Okay. So however, divers who go deeper than 5 meters have to learn to equalize the pressure inside the ear. Okay, this force you can bear. Okay, so the 3 newtons, this is not an extremely large force, but it makes sense because you can dive to a depth of 5 meters or 18 feet without rupturing your eardrums. However, divers who go deeper than 5 meters have to learn to equalize the pressure inside the ear with the external water. So the lungs have air at higher pressure, and you want to equalize the pressure here. Okay. And the way you do that is this eustachian tube is normally closed. They can do so by pinching their nose and blowing gently to force open the normally closed eustachian tube. The internal pressure of your ears spontaneously equalizes with the external pressure, because the air in your lungs is at high pressure, which will increase the pressure there. Okay. So that's what you need to do when you go diving or when you go underwater. You close your nose and blow hard and open your eustachian tube. Is there anybody a diver here? Does anybody dive? Okay, so you experienced doing this? Mm-hmm. So you're free diving or you're scuba diving? Yeah. What's that?
So it wasn't spearfishing now on scuba.
Mm.
You don't want to be caught scuba diving spearfishing in certain parts of the world.
Where? Sir?
Look at Matt, you get caught scuba diving and spearfishing.
Oh, I see.
It's not sporty.
Oh, I see. Yeah. Well, so there in some cultures there are free divers who hunt for pearls and stuff like that, and so they automatically do all of that. Okay. So you need to learn to blow the high pressure air in your lungs into the inner ears so to balance the pressure. Okay, so now we'll talk about hydrostatic equilibrium. So liquid at rest, this is not possible because the pressure, it turns out that in a horizontal line, the pressure depends only on depth. So the pressure everywhere on a horizontal line is the same in a fluid. So the pressure here is atmospheric pressure, but the pressure here would be atmospheric pressure plus the pressure of this column. So the higher pressure would push this liquid back in this direction. Okay, so in equilibrium, this is not possible. The water level would come to the same level everywhere. Again, but you know this. A connected liquid in hydrostatic equilibrium rises to the same height in all open regions of the container. Okay, so now we'll define gauge pressure. Okay. So for instance, when you measure your blood pressure, let's say your blood pressure is 120 by 80, that 120 millimeters of mercury, that's a gauge pressure. Okay. What a gauge pressure means is the actual pressure, the gauge pressure means the actual pressure minus the atmospheric pressure. So what is the pressure in your tires, in your car tires? About 30 psi, we'll say 30 psi. That is a gauge pressure. The actual pressure in your tires is 45 psi minus the atmospheric pressure of 15 psi, which is 30 psi. Okay. Why do we define something like this? Because instruments like this are actually not measuring the actual pressure. They're measuring the actual pressure minus the atmospheric pressure. That's how they're designed. And so that's why we define this. Okay. So the gauge pressure is the actual pressure minus the atmospheric pressure. So the actual pressure in your car tires is really 45 psi. Okay. So whatever if your car tire is set to 32 psi, you just add 15 psi to get the actual
Is
pressure.
your thing supposed to be doing that?
Sometimes it does that. It has a delayed reaction. When did it start? Just now?
I just noticed it now.
Okay.
Yeah, you had the gauge thing up like 30 seconds ago, now it's going all replaying the screen recording.
I know it's been doing that.
You just wait for it to catch up.
What's that?
You wait for it to catch up.
Yeah. Well, do you know why it might be doing that? It seems to be resetting and.
You got a screen on
What's-
your tablet, sometimes it presses it.
I'm sorry?
If you have a screen on, like on your phone or something, you
Oh.
have like a protected thing, sometimes it like presses it.
No, I don't have a protected thing.
Um,
But also, I mean, I wonder where is the memory? It's replaying from, it's buffered, and so the buffer is playing. Anyway, all right, so these gauges are designed to measure the pressure minus actual pressure. So, by the way, so atmospheric pressure is 760 millimeters of mercury. So when you measure your blood pressure and you say it's 120 by 80, this is in millimeters of mercury. Okay, this is the systolic pressure or high pressure when your heart pumps. That's the pressure at which the blood is, but that's a gauge pressure. So the actual pressure of your blood is 760 plus 120. Okay, it's 880 millimeters of mercury. All right. So anyway, most instruments are designed to measure the actual pressure minus atmospheric pressure. Okay. Blood pressure cuffs and many pressure gauges, such as tar gauges, measure not the actual or absolute pressure, but what is called the gauge pressure. Okay. So it's the absolute pressure minus atmospheric pressure. So you just need to be aware of that. Okay. We use a barometer to measure atmospheric pressure. Yeah, go ahead.
So, just going back to tire pressure on the gauge thing,
Mm-hmm.
you fill your car tires up to 30 psi in
Mm.
Denver,
Mm-hmm.
and you drive down to Miami.
Mm-hmm.
The internal pressure of the tire hasn't changed, the external pressure has, so then your tire pressure would show lower on the gauge?
Yep. So you filled it in Denver, and you come to Miami. Well, so let me think about this.
Tire's flexible though, so.
Right. So, oh, well, you fill that to 30 psi, it'll be 30 psi here too. You're filling, the psi is the internal pressure that's measuring. When you come to Miami, the external pressure is larger. So let's do a balloon. You take a balloon, fill it up to 30 psi in Denver, and then you bring it to Miami. The external pressure is increased and the balloon shrinks a little. That's all.
So it just makes the tire more small.
Yeah, that's all. Yeah. Okay, a barometer is something that measures atmospheric pressure. Okay, you might have seen these in chemistry labs and stuff like that. So here's how you make them, and you use mercury to make them, and we'll tell you in a second why you use mercury. Okay, so you fill a tube with mercury, completely fill it, and put your thumb on top of that, and then you invert this tube in a pan of mercury. Okay. And what will happen is, okay, so this tube had better be bigger than 76 millimeters, 760 millimeters, or it needs to be about 1 meter tall. Okay, so about this tall, 1 meter tall, greater than 76 centimeters, yeah. Greater than 3 feet, greater than 2.5 feet. Okay. And then you invert it, and this column will be 76 centimeters or 760 millimeters. This is a perfect vacuum. That's the way. So this is one of the perfect vacuums that you'll see here. Okay, so you can create a perfect vacuum without using a pump. Okay, and what is happening is this column of mercury is balancing this column of air all the way to space. So this weight is being balanced by that. That's the barometer. Okay, and so it's reading atmospheric pressure at this point, and this is 760 millimeters of mercury. Okay, if you made a and this the weight of this column is density times G times H, where H is the height. Okay, the density of mercury is about 14 times that of water. So if you made a barometer with water, this would be 10 meters. It would be twice the height of this room. It wouldn't fit in this room. Okay, so to make a barometer, you have to use a high density liquid so that the height is not too high. Okay. So that's why mercury is used. Okay. Okay, so like I said, if it was, so this is atmospheric pressure supporting this column of water. And if you made a barometer with water, this would be 10 meters tall. Okay, so let me show an application of that. So atmosphere, so if this, you had a vacuum here, atmospheric pressure could push a water column 10 meters high. That's what it can do. Okay, so you guys have seen hand pumps like this. Okay, they pump water. So here's how they work. Okay, what the hand pump does is, so it has this diaphragm, and when you pump down, this diaphragm goes up, and what it's doing is it's creating a vacuum here. And if the vacuum was perfect, so here's the water table, here's water, and there's atmosphere pushing down on the water. So if you created a perfect vacuum, this atmospheric pressure would be able to lift the water up to a height of 10 meters. That's the maximum it can do. And so if this is a very good diaphragm and you're creating perfect vacuum, then you can pump water from a depth of 10 meters. This water would come up. Okay. So what you're really doing is creating a vacuum here and letting the atmosphere push the water up. Okay, so that's how this works. So but suppose you have a powerful pump that can completely remove the air. So a powerful pump just means it's a very good seal and it creates a perfect vacuum. Then the water will rise to a maximum height of 10.3 meters. Okay. So these work only where the water table is low. Fairly high. Okay. So you can't use these pumps where the water table is, let's say, 20 meters deep. Okay. What is the advantage of this thing? A hand pump like that, see all this, everything is sealed. So if the water table is deeper, then what do you do to get water? You have to dig a well. Okay. And that's what people did in villages and stuff like that. Okay, so here are some of the pressure units. Pascals is the SI unit, and it's Newton per meter square. And atmospheric pressure is 100,000 pascals, 10 to the power of 5 pascals. So here's in the medical field, in your doctor's office, they use millimeters of mercury as the pressure. Okay, and 1 millimeter of mercury is 133 pascals. So this is a conversion in case you need to do that. If you've gone to an ophthalmologist and they measure the pressure in your eye, that's about 14 to 15, and that's also a gauge pressure. Okay, that's in millimeters of mercury. Okay, and when you're filling air in your in your tires, you use the PSI, pounds per square inch, and 1 PSI is 7 kilopascals. Okay. Okay, so these units arose historically as scientists and engineers worked on different subjects and developed units convenient for them. Okay, so whatever field you're working in, you develop units that are convenient for you. Okay, so in a doctor's office, they use this because they don't want to express pressure in pascals, that those numbers are big. we don't have a tendency to be able to remember big numbers. In millimeters of mercury, those are small numbers, and you can remember those. All right, so here's oil and water. So let's see what is possible. Oil has a lower density than water. And so in a liquid, the pressure depth is rho GH, okay, for at the bottom of a liquid. So lower the density, lower the pressure. Okay. Remember, the pressure in a horizontal has to be the same. The pressure at this point has to be the same as this point. This is not possible because this pressure, the pressure due to this column would be less than this column. And the pressure is higher, and that would drive water in this direction. Okay. This is not possible again because this pressure would be lower than the pressure at that point. So only this is possible because this pressure is probably being balanced by this pressure. So if you put oil and water like this, oil would be at a higher level. Okay. Again, the deal is, so for a liquid, the pressure at the bottom of the liquid, that's the gauge pressure, is the density of the liquid times G times the height to which you've gone, or the depth to which you've gone. Okay. Since the density of oil is lower, it has to be a higher column. If you have this lower, it has to be a higher column to give you the same pressure. Do you guys understand that? Okay. Okay. If you go underwater, you feel an upward force, and that's called a buoyant force. Okay. So for instance, if you weigh yourself on a scale, you get whatever your weight is, let's say 160 pounds or whatever. Now, if you do the same thing underwater, okay. Again, so okay. So what's happening here is gravity is pulling you down, and this guy, your scale is pushing you up. Okay. So when you're weighing yourself in air, gravity is pulling you down, and the scale has to push you with an equal force. And that's what you feel as your weight. Okay, now let's do the same thing underwater. So if you do the same thing underwater, well, gravity is still acting on you, but the water is pushing you up. That's called a buoyant force. And so this scale doesn't have to push you up. So if you weigh yourself underwater, the scale, it'll essentially read 0. So if you want to lose weight, just weigh yourself underwater, and you'll be weightless. Okay? So now what we want to do is understand this buoyant force. How is the water pushing you up? Why is the water pushing you up? Okay, so you saw that the pressure increases with depth. So the pressure here is lower than the pressure here. The higher pressure exerts a greater force, and this force is greater than that force. And this difference is the net upward force, which is the buoyant force. So if you immerse yourself in a fluid, you feel an upward force, the buoyant force. Okay. So the reason for buoyant force is the pressure in a liquid increases with depth. So the pressure at the bottom of the cylinder is greater than at the top. And so this force is greater than that force. Okay. And that's, okay. So the pressure in the liquid exerts a net upward force on the cylinder. Okay. This is the buoyant force. Mr. Archimedes told us how great this force is. He told us exactly the value of this force. Okay, and that's the Archimedes' principle. And it turns out that this upward force is equal, so this object displaced this much water. This upward force is equal to the weight of the displaced water. So if you displaced 100 pounds, the upward force is 100 pounds. If you displaced 1,000 pounds of water, the upward force is 1,000 pounds. That's what Mr. Archimedes figured out. Okay. buoyant force, okay, so a fluid exerts an upward buoyant force on an object immersed in or floating on the fluid. The magnitude of the buoyant force equals the weight of the fluid that is displaced. And that's Archimedes' principle. And so here's the formula for it. The buoyant force is the density of the fluid times the volume of the fluid that was displaced times g, the gravity, acceleration due to gravity. Okay? So the buoyant force is equal to the weight of the fluid displaced. Okay. All right, so let's figure this thing out. Okay, so they all are immersed in a fluid. They'll all feel an upward force. Okay, so which one feels the greatest buoyant force? Let's just talk about the greatest buoyant force. Which one will feel the greatest upward force? So there is the volume of this object that displaces 10 cc of water. This displaces 10 cc of water. This displaces 10 cc of water. This displaces 20 cc of water. This displaces the greatest amount of water, and so it'll feel the greatest buoyant force. Okay? The buoyant force is just the upward force exerted by the water. And whatever has the greatest volume, okay, this will feel the least buoyant force. Okay? All these guys will feel the same buoyant force. Okay? Now this happens to be heavier than these guys, so it's the weight is greater than the buoyant force, and that's why it's sunk. Okay? So now let's figure out what will float or sink. So let's figure out what is it that the criterion for floating or sinking. It turns out that, so if you sink, that means the weight is greater than the buoyant force. If you float, that means if you float up, that means the buoyant force will be greater than the weight, and so you'll rise up and it will float. And if you're immersed and if you don't move, that means the buoyant force is equal to your weight, and so you'll be suspended in water. And so the condition works out. If you're sinking, then the density of the object is greater than the density of the fluid. Okay, so here the book writes average, but I'll say the density of the object is greater than the density of the fluid. If you float, then the density of the object is less than the density of the fluid. And if the density of the object is equal to the density of the fluid, neither will you sink nor will you rise. You'll stay suspended. So in fact, you can breathe in air, take a deep breath. Normally your density is a little higher than the density of water. So if you take in a deep breath, then you can reduce your density and you could float. You can stay immersed in water. And if you don't panic, you won't sink and stuff like that. Okay. An object hangs motionless if it weighs the same as the fluid it displaces. Okay, so there's the conditions for floating or sinking. Okay. Okay, so when an object is floating, the buoyant force has got to balance the weight. And what is the buoyant force equal to? It's equal to the weight of this displaced fluid. Okay. When an object is floating, the density of the body, the density of the object is less than the density of the fluid. Okay. So here's the weight of the object. The buoyant force needs to equal this. And so the weight of this guy, this much fluid, is equal to the buoyant force, is equal to the weight of the object. What this formula gives you is the volume of fluid displaced this volume. The volume of fluid displaced, that is the density of the object, density of the object. Remember, if the object is floating, its density, the density of the object, okay, so the density of the object has to be less than the density of the fluid. So the volume of the fluid displaced is the density of the object divided by the density of fluid, which is, this number is less than 1, times the volume of the object. Okay, so this is the fraction of the object that is immersed. All right, let's look at icebergs. See, the density of iceberg is 917 kg per meter cube. That's the density of the object. And the density of seawater is 1,030 kg per meter cube. See, the density of fluid is greater than that. All right, the question is what volume of the iceberg is underwater? Okay, so the volume displaced, the volume of water displaced is the density of the iceberg times the density of seawater times the volume of the iceberg. So this tells you the fraction underwater, and that's 89%. So 89% of the iceberg is underwater. Okay. So the captain of the Titanic knew this. You never get close to an iceberg. You don't know what the shape is underwater. So so what's going on with boats? Okay, here's the weight of this boat. Okay, here's the weight of the boat. And so for a boat to float, the buoyant force has to equal the upward force which exerted by the fluid this force has to equal this force. Okay, so what happens is the boat sinks to a point where the weight of this displaced water, which is equal to that, is equal to the weight of the boat. So the weight of this displaced water is equal to the weight of the boat. So heavier the boat, the deeper it has to sink. It's got to displace more water, such that the weight of this displaced water is equal to the weight of the boat. Okay. So, I'm sorry?
So we got a spread out boat, and that's so that the sink farther, it has to cover more area of displacement.
Well, so if the boat is wider, it sinks less. If the boat is narrow, it sinks more. So what will happen if you invite some friends on this boat? As they get on the boat will sink more. How much more? If you invite 10 people, it has to sink enough where the weight of the displaced water is equal to the weight of those 10 people. Okay? So that's what happens. Okay? The upward buoyant force then balances the weight of the boat, and the boat floats in equilibrium. And of course, in this boat, you got to design the boat such that if you have all the people here, you don't want the boat tipping over, so you have to make sure that it's stable and all that. Okay? So the keel is heavy. Okay? All right, we'll stop here today.